geometric perspectives, transverse theory for Lie group actions. Please.
Thank you. So can I start?
Yes. Yeah. Please.
Yep. Okay. Yeah. I wanted to thank you very much for the invitation to speak here. So how to say? So I hope the talk will be somewhat in line with the topics of your conference, because it's so basically I chose to make a survey in here. So a lot of the analysis will be pushed under the rug. So a lot of this also will have to do with what's called KK theory. So I'll try to give also some overview of what it is for people who are not familiar with that. And so basically a lot of the technicalities will be sort of hidden, but I'll try just to outline the main ideas basically. So here's the outline of the talk. So first we'll just review Kasparov's formulation of the index theorem, so the classical one, just to give some ideas of basically how KK theory is used and what sort of what it means in terms of geometry. And then we'll go into his formulation of so Kasparov developed very recently some formalism to tackle the index theory of transversely elliptic operators for group action, for Lie group action. And then, so time permitting, we'll try to go further. So examples and application is like my own work. So there is some relation to from the perturbed Dirac operators. That's kind of interesting. So we'll try to talk about that. And then time permitting, we'll see that we'll talk briefly about what's the relationship between Kasparov's work and what Berline and Vergne had done in the 90s. Okay. Okay, so what is KK theory? So just brief review of K theory before that. So we begin with just a locally compact space. And basically, so K theory is about finding topological invariants through vector bundles. So so the reason why vector bundles are good candidates to get topological invariance, it's because simply if you have two, so there is a little theorem saying that if you have two vector bundles that are basically homotopic, then they're actually isomorphic. So there is some kind of stability in this regard when you consider these objects. So basically, so here it's a more refined version of K theory that was that I'm using that was introduced by Atiyah. So here so basically elements of the K theory of X will be represented by pairs of bundles like that. So let's say two vector bundles, E plus and E minus. So very often they will be part of one same vector bundle, and that will be very often the even part and odd part in quotation marks. So for example, if you take an external algebra bundle, so that's the case. And then so you ask also for an operator sigma, which acts on the sections on the bundles. So it's basic. So sigma here. You ask also that it's an isomorphism outside a compact set. So here it acts on sections of the bundles here. So what you should think about here, so if you don't know about this kind of stuff, so it's that, so sigma here is meant to encode what you have with elliptic operators, basically. So so if you see in here, so if you have an elliptic operator, you are in these conditions here to have an isomorphism between these two bundles outside some compact set on the base space. So basically it's precisely made for that. So the motto here is to say that if you use you can use basically topologically symbols of elliptic operators to build vector bundles as so using them as clutching functions if you want. So that's that's the upshot of this definition here. So one example is this here. So important example, which is called the bot generator. So here we just take the space, so it's R2n basically, but prefer to see that as the cotangent space of Rn. So the space is that. So in the K theory of T star of Rn, and then we take bundles of spinors, and with Clifford multiplication that acts on that. So when you take Clifford multiplication, that's basically the symbol of the Dirac operator on Rn also. So here, how do you build a vector bundle out of that? So basically here you have to think, so here T star of Rn, it's like R2n, so you just take a disk, take a disk that inside of T star of Rn, and then you have a trivial bundle here over the disk. Then you have here another trivial bundle, the same over the disk. But then you have an isomorphism between the two bundles here, W plus and W minus. It's so here it's really as long as the covector is not 0, and so you have an isomorphism between the two via this the Clifford multiplication, as long as you can take a non-zero covector. And then from that, so what you can do is so build a vector bundle on a sphere of dimension 2n by just clutching the two disks over their boundaries. And for the vector bundle, you can glue them just using the isomorphism here. So you have two disks like that, and then you clutch like that. So I should have made a picture, but I didn't want to overload the slides. And from there, so an important theorem from there is like bot periodicity theorem, so which says that you can send the K theory of the point, so which is just Z, because vector bundles over the point, it's just vector spaces, so they're classified by their dimension. And then you multiply by the bot generator, and you end up into the K theory of T star of Rn. But so then the bot periodicity theorem tells you that this is an isomorphism. So basically here, the K theory of R2n, that you have here, is actually Z. So that's what it says. Okay, so that's for K theory. So you have this kind of thing. So remember here we have triples like that, triples like that, with vector bundles, and let's say something that's like the symbol of an elliptic operator, basically. So that's made for that. So one way to prove this bot periodicity isomorphism, so we'll come to it a bit later. But the technology, one possible way to get that is to introduce cohomology. So it's not the historical, the first proof, but Atiyah later found a different proof using basically duality. So here K theory is basically a homology theory, and so there is an associated homology theory which is called cohomology. So which goes this way. So simply. So and here the upshot is really, I mean, I don't think Atiyah was the original motivation of Atiyah, but that it ends up being one consequence here, that we can construct an inverse of the bot map with duality this way. So the idea is this. So basically you have K theory, which is like triples, like that, like we said before, and it's an operator acting on sections of the bundle. But now, so if you think about these functions here, these endomorphisms that you have here as symbols of elliptic operators, then you may consider their Fourier transforms instead, and then you get the actual operator with that. And so here, that's what cohomology is basically. So you basically take the Fourier transform of this definition here, and instead of considering just the symbol of the elliptic operators, then you consider the elliptic operators themselves. And they act on some Hilbert space instead. So in here also normally there is some kind of subtlety. So here I took the elliptic operator right away, but normally there is some kind of normalization to reduce that to another zero elliptic operator, and then it becomes a bounded operator on L2. So But here I just omitted this kind of fact. So if you're picky with that, you should think that all the operators here are normalized, actually. Okay, so an elliptic operators, as you know, they are invertible up to compact operators. And so now we have the two theories, so which are cohomology theory here and homology theory in here. And there is a pairing that's associated to that this way. So simply, so if we have a vector bundle and in here E, and we have in here D, so that's a elliptic operator. Then there's a construction where we can twist the operator to make it act on E. And then it turns out this operator has an index, and you can take its index here. So we can you have a pairing that goes this way. So here I denoted also this pairing as a kind of tensor product. That's because, so we'll see later, in Kasparov's work on KK theory, there is something called the KK product, and this is a particular case actually of that. Okay, so and basically in here, so we'll see the proof a bit later when we'll talk about KK products. Okay, so basically what happens here is that if you want to go from, so the bot map was going from Z to the K theory of that. And if you want to get the inverse, so from the K theory of that to that, so you just have to pair with, use the pairing that's above and pair with the Dirac operator on R2N. So, and then you get, you'll get the well, so, and that gives you this inverse. Okay, so now we can take steps a little bit further. So maybe just to go back in here. So basically here, if you pair the, so there is, if so there is a sort of, you see duality between K theory and K homology already, just on R2N if you want. So you can take things a little bit further, and that's a theorem of Kasparov, which says you'll consider this pairing between K homology and K theory. And then what he says is that, so the one formulation of the index theorem, basically, so it's not an easy theorem, so it's a good deal of work. But what he says here is that, so let's say you have an elliptic operator on a, let's say on a compact manifold here, to simplify things. But then he says that basically you can, so one way to get the index here is to pair the symbol and some elliptic operator on the cotangent bundle. So here it's an elliptic operator on the entire cotangent bundle. So here that's the D bar is the Dolbeau operator, and you take its adjoint here. And so if you take the sum of the two, that's an elliptic operator. So this pairing here gives you the index. So here you have a sort of interesting thing that pops up already, which is because already, so you see that basically you have here A is like any elliptic operator. Order 0 if you want, but let's say that's any elliptic operator. But here what you're actually doing is to reduce the index of A to basically the index of some Dirac operator. So that's if you want Kasparov's Kasparov's theorem in here, it's a very clean way to make this reduction of any index to the index of a Dirac operator. So that's one thing. So the other thing, so we'll get back to it a bit later. It's the fact that actually, so this product with this element here, it's basically the topological index of Atiyah and Singer. So you need a little bit of work to do that. So we'll try to explain this point a bit later when we'll talk about products. So basically this equality here contains almost the whole Atiyah-Singer index theorem. So just before getting into that, so just a couple of words about non-commutative geometry, because that's the heart of these techniques. So that's of these techniques here. So the idea is simply that, so in NCG, so non-commutative geometry, you replace spaces by their function spaces when you study the spaces instead. So you take function spaces instead, And eventually, sometimes you may end up with studying some non-commutative algebras instead, C-star algebras very often. But then, so if you have, so if you in this context, so here B is a C-star algebra. All the definitions you had before, they generalize very easily. So there is no problem in generalizing the definition you had before. So here you have to think about, okay, so you see basically in here, so K0 of B, it's like a triple again. So here you have a Hilbert module over B, and you should think of that as sections of some bundle basically. And then, so here in this case of K-theory, and then you have still this operator that's invertible up to compact operators. So in the sense of Hilbert modules here. But what that means here, so you should think of that as like the case you had before. So you have an endomorphism that's invertible fiber-wise, if you want, outside some compact set. Basically, it's one way to think about this. Then cohomology also generalizes very easily. So the notion of Fredholm operator also makes sense in this world. So, and you ask for certain conditions about compactness. So here, so the fact that you're a Fredholm, let's say, so you just change that to a sort of normalized condition, saying that the square of the operator will be -1 will be compact. So here and so here it's the same kind of thing. So you have a Hilbert space here, an operator here. Yes. Was there a question? Or okay. So, but it's basically the same definition as when you had a being a continuous function on a space here. So and so basically, so when you have these definitions here, so if you want to get the K-theory we had before, you have to take B as B or A as continuous functions on some space. And that recovers the definitions you had before for when you had spaces before. And then, so the next level is KK theory. It's just about combining the two suitably. So here we have some Hilbert module over B in here. So it's a mixture of the two exactly. And then here you have some kind of Fredholm operator, but in the sense of it's compact. So you have the same conditions as above. So F square -1. So it's like ellipticity in here in some rough sense. Being a compact operator, but modulo the algebra B. And some condition about combinators like this. So one way I like to think about this here. So what is KK of AB? It's basically like a relative version of K of these theories that you had before, but relative to morphisms, if you want. So if you want to think about this, a very good element to think about here would be, so if you have a fibration, over some base space, and then over each point of the base space, so you have an elliptic operators that act on the fibers, and basically, so we saw before cohomology elements were basically elliptic operators. So these things are meant to encode families of elliptic operators over some base space, let's say. So roughly, it's the definition is made for that to handle families of operators. Okay, so and a difficult theorem, which is so just before we had seen a kind of product between K-homology and K-theory. And actually, you can take steps a bit further, which is so in KK. So here A and B are C-star algebras also. And then so you can theories like that, you can combine them to get an arrow like this. You might think of so if you want a sort of example like that, if you want. You can think about family. It's like the example I just mentioned before. So it's like families of operators, if you want. And imagine families of elliptic operators. And roughly, a naive idea would be that you can take the index of each operator on each fiber. basically. And if you do that, then you end up with an element in the K-theory of the base space. And so that's basically, if you want, this product is basically doing that, if you want. So it's made to encode this kind of idea. Okay. So here's an illustration of products in some geometric situations to give some flavor of what this means. So here I'm taking a compact manifold. And so here I'm changing a little bit the function space. So instead of taking just continuous functions on the manifold, I'll take sections of the Clifford algebra instead. So once you are in here, so you can replace that by some extra algebra bundle if you want also. So that's the same thing essentially. But then, so here, then you have different elements. So here you have one element here, which is an element of cohomology. So here, yeah, I haven't said, but basically also very quick. So when the entries, so here the entries are A and B, two C-star algebras. But when the entry A is C, then it means it's the K-theory of B. And when the entry of B in here is A, it's the cohomology of A. So that's what we have here. And if you have A and B function spaces, like continuous functions, so for example in here, if you have B equal to C of X, so I think I mentioned before, but quickly, if B is C of X, then this is really the K-theory of X at the end. So you consider here the class of the Durham operator. And so what happens here also is that if you take a vector field with a finite number of critical points. In here, and basically this gives you a K-theory element in this algebra. So I think you might have already heard that when you take the Durham operator, basically the index theory of the Durham operator will give you the Gas-Bonnet theorem, basically. So that's sort of the part what's mentioned here. So if you have this part, then if you have this kind of thing, then the product between the two, okay, so it's a number, and that's actually the order characteristic of the manifold. So it's somewhat a form of Gas-Bonnet if you want. But then, so you can go also a tiny bit further. So if you pair with here with the vector field. So here what's interesting is that there is a kind of exigent process that goes on. So you can basically localize the calculation that you have here of this index to the critical points of the vector field. So that's something called excision in K-theory. So what happens here is, so as in the picture in here, so what happens, you can refine a bit this calculation and get the Poincare-Hopf theorem. So it goes this way. Basically, so when you calculate the product here, okay, so just to explain that it's really the order characteristic first. So when you calculate the product here, what you can show is that the product here is represented by some operator of this form. So it's like a Perturbe-Dirac operator. So D plus D star plus some potential here. That's one thing. But then, so on the other side, so since you have this product here, you can basically localize just on this side. So this side contains all the topological information. You can localize here just to these critical points. And then, so once you did this localization here, it's not hard to just boil down to the index of the vector field from there. So that's basically the idea. So you can localize to any arbitrary neighborhood of the critical points. So if you want and basically KK theory allows if you want to separate the analysis and the topology directly. So in this case, so here you have topological properties of the vector field that you can localize, and here you have the operator. Okay, so what's the next example? So just to get back to bot periodicity that we had before. So basically, you can also prove bot periodicity that we had before as via the index of some perturb operator. And so what you can show, so before we had the bot map and we had the inverse that we described before. And taking the product, okay, so we showed that normally this has to be the identity. So one way to show that is that, so in KK, so when you take the product here, you can represent that by the operator D, so that's the Dirac on R2N, plus I times, so plus basically the Clifford multiplication, that was the symbol of the symbol of the Dirac. So if you square that, you take the square of that, and you can easily see with a little calculation that it's basically a harmonic oscillator, and for that reason it has index 1. And so once you've shown that, then so there is a classical KK argument that tells you that if you have some index 1 operator, then you can homotope that to the unit in KK. So I haven't described exactly what's the unit in KK, but basically there's a it's basically represented by the 0 operator. But you can homotope that. So it's a basic principle in KK. So I won't get into much more details here. But that's kind of where you see that the analysis comes in this world. So here we have some harmonic oscillator and some perturb operator already, and so we'll see these kinds of things. They come throughout. So there's another example also, which is what we call Thom isomorphism. And so here we'll see the relationship between Kasparov's index and the topological index. So basically, so I'll say very briefly, but if you have a normal bundle here, if you have an embedding here, then you have a normal bundle, and then taking the tangent spaces, you also have normal bundles. So then the tangent space of the normal bundle, it can be endowed with a complex structure because you have this kind of splitting here. And for that reason, you have you have this structure in here. So a fibration Tn over Tm, and over the fibers you can have Dirac operators on the fibers. So and then you have here a family of Dirac operators over Tm. So and basically what you can do with the bot periodicity that you had before, so you can do that in families with and do this kind of calculation fiber-wise if you want, that the thing we had done before, and that's what the Thom isomorphism is. And you see that if you do that, basically you're basically shrinking all these fibers to points, and you see that the K-theory of Tn will be the same as the K-theory of Tm. And so the way to make it work is very natural, actually. So you have families of bot elements on the fibers here, the ones we had seen before, but a family over Tm. And then you have families of Dirac operators on the fibers also, same thing. And then, so if you multiply the two, then basically you get, so on every fiber you have index 1. And then basically you see that you can pass from the K-theory of Tn to the K-theory of Tm this way. And so the way to make this precise is a theorem of Kasparov again, which is to say the following thing. So roughly a Kasparov product, it resembles to something like that. So you have F1 tensor F2, which is roughly F1 tensor 1 plus 1 tensor F2. So I'm lying a little bit here. But there are some technical complications if you just do that, but you can basically modify. So just to get ideas, that's basically it's okay for the talk, I would say. But then, so if you take the products that you had before, so that's the products we had before. So the families of Dirac times the families of Bot, that's 1. Families of Thom times families of Dirac, it's 1, but on the other algebra. And so there is also something interesting, which is like the fact that, so now we have a fibration. Maybe I'll go back to the picture here. But the fibration, so we had this family of Dirac here on each fiber. And so basically, if you do, what happens if you do the product of a Dirac on Tm and these families of Dirac? And so if you do, if you do this calculation in here, so product of that on the fibers times product on the base, then you have an elliptic operator on the whole thing. And cohomologically, what you get is actually, so if you do this product, it's actually the Dirac on the whole T of RD. So that's a particular case of the families index theorem here. And you see that there's something very interesting about the product. That's basically, it allows you to have some structure, geometric structure like a fibration that's basically splits the space in different parts, fibers and base. And KK theory basically allows you to split elliptic stuff in terms of these two elements here, fibers and base. So that's the content of this equality here. So D of Tn, the whole Tn, is basically the product on the base and the product on the fibers. And from there you can, so the topological index of Atiyah and Singer, you can basically formulate that with just these products. So it works this way. So the topological index of Atiyah Singer, you have K of Tm to K of Tn by the Thom isomorphism described before. Then Tn, it's basically an open set inside of T of Rd. So by excision, it's actually the same as T of Rd. And then you can take Bok periodicity to get there. And so you see every of these maps, you can formulate them in terms of products. So here you multiply by the family of Bott elements. Here you multiply by the family by the Dirac operator. And then so you can basically reprove the index theorem from Kasparov products. So you just write, so here this is Kasparov equality. You just separate that in terms of what we had before. So you can do that because you just shift this thing because this is 1 from what we saw before in here. So this is 1 and you shift that in the middle. And then so you see that here, if you take all these products, it's basically the composition that gives you the topological index. So if you have the existence of products, basically you see that you have a very powerful tool that just allows you to do these things conceptually in a very satisfying way. In particular, also it means that the topological index, it's like the index of this operator here. So if you think of that as families of Bott elements, so it's like you can make these things as you can see these things as perturbations of this operator here. How much time do I have still?
7 minutes.
Okay.
Together with questions, so maybe it's 3 minutes.
Oh, just 3 minutes?
Yes.
Oh, okay. So I'll have to, okay, so I'll try to explain because I wanted to get to, okay, so very quick. So so basically now the thing is that with so Kasparov's technology allows you to do much more actually, and you can do basically things with the transverse elliptic operators. So basically here I have some action of a compact group, and then and then from there, so you just consider ellipticity that's transverse to the orbits of the group action. So you just consider ellipticity this way, and so if you go this way, so Atiyah had said that you can basically have a topological, you can define an analytic index with that, but he didn't have a topological index. So that's the point. So what's the idea of Kasparov at the end? So the idea of Kasparov is to introduce some algebra, which is like a sort of, so I'll be a bit, I will outline very quick, but it's basically a Clifford algebra that goes only in the orbit directions. So this is what's here, basically. And so once you have this kind of thing, then what you can do is you can formulate an index theorem from Kasparov the same way as what you had before. It's a bit more complicated, but it basically works the same as for the. It basically works the same as for the classical index theorem. So it's a bit more complicated, but it's a very similar product. And then, so what happens here? So the heuristic behind that is that, so basically, you have a transverse operator. So basically, you can. So the algebra that you have just allows you to. So it allows you to add variables on the orbit part to get something that's elliptic. So that's what the symbol here is for. And basically, that's what Kasparov's theory allows you to do. So you can just reduce basically the index theory of transverse elliptic operators to just elliptic operators. So that's basically the upshot here. So here I have a little example on the circle action, but won't have time, I think. But then there are other things you can do. So I'm giving here an example of transverse operator. So here is okay. So here, so I'll try to wrap up with this. Okay, so here the context is here. So here you have a moment map for the group action that we call new, and from there you can build a vector field that just goes in the orbit directions. So now you take the symbol of the Dirac operator and you perturb with this thing in here, with this orbital Dirac orbital vector field. Then this way you get a transverse elliptic operator. And so what I had shown recently was that, so basically, so you can compute the index of this operator using KK theory. So normally it's something that's work of Paradan and Vergne, and they did that to solve a sort of old conjecture of Vergne, which is like something called the quantization commutes with reduction, but for non-compact manifolds. So that's what I have here. So if you can compute this index, that's basically you basically solve the Vergne conjecture, which is quantization commutes with reduction for non-compact manifolds. And then their page, so they basically they have a sort of fixed point formula that takes this form in here. So what's interesting is this. So just to wrap up here, so that I have a proof of their formula. So their proof basically takes I think something like 30 pages. But if you use Kasparov's technology, it basically takes, so if you have the background on KK theory, it basically takes 2 pages. So just to show basically how powerful the Kasparov's tools are, if you want. It's also at the cost of some sophistication because you use KK theory and this kind of stuff. But you see that geometrically, it's not too hard to grasp, I think. So I think my time is up. So, but if there is time for questions and you want me to go back to something, then I'll be happy to say more. Thank you very much then.
Thank you. Maybe question. Questions?
So for this formula, you have a new proof, yes?
Yes, I have a short proof basically. So the point is really, so how to say, if I can explain at least the main points. So it's the fact that so Paradan and Vergne, they have a lot of difficulties because they are using basically Atiyah and Singer's technology from before. And so there are things that they don't have access to and they have to do by hand. So basically, for example, in the world of transverse elliptic operators, you have some Thom isomorphisms, but it's more complicated to write because of the group action. The fact that the group action make the dimensions of the orbits jump and everything. So the geometry is a bit complicated. So they managed to do a kind of Thom isomorphism by hand, but it's kind of very lengthy and technically it's a bit hard. But if you're in KK, you basically have this kind of thing automatically. So that's the point. And also so Gennadi's, so Kasparov's algebra makes things very easy to handle. So that's the other thing.
Did you already publish this? Or
It's
is it
on archive. It's on
or
archive.
not?
Yeah, at least. So it's on archive. I think I made a couple modifications on the last version, so I have a more recent version, but I'll try to put that on archive as well. So it's not much more. So
Thanks a lot. For our last talk today, this speaker already